as I mentioned that in place of considering location alternative or the scale alternative, one may consider general alternatives. That means, we simply say that the two distributions are not the same. So, now an analogous situation you can think of in the case of parametric or non-parametric situation is that we may think of not specifying the distribution and then talking about the location parameter or the scale parameter. Rather, we consider simply the specification of the distribution itself. Now, in the one sample problem, one solution was given by the chi-square test for goodness of fit, and another solution is given by the Kolmogorov-Smirnov test statistic. Now, let us define the general two sample problem and discuss the analogous tests here. So, the general two sample problem is so let x1, x2, xm be a random sample from a continuous distribution fx, and say y1, y2, yn be another independent random sample from a continuous distribution gy. Okay. So, we want to test the hypothesis whether gyx is equal to fxx for all x against the alternative gyx is not equal to fx for some x. For this problem, one of the you can say most plausible solutions is the Kolmogorov-Smirnov two sample test statistic. So, let us define firstly the empirical distribution functions based on x1, x2, xm and y1, y2, yn. So, let fmx and gnx be empirical distribution functions based on x sample and y sample respectively. So, we are defining like fmx is equal to 0 if x is less than x1, it is equal to I by m if xi is less than or equal to x less than xi plus 1, for I is equal to 1 to m minus 1, it is equal to 1 if x is greater than xm. Similarly, gnx is equal to 0 if x is less than y1, it is equal to I by n if yi is less than or equal to x less than yi plus 1, and it is equal to 1 if x is greater than or equal to yn. Then dmn, that is equal to maximum of fmx minus gnx. If you remember, in the case of one sample problem, it was defined as fnx minus fx. Here now I am considering the difference between the distribution the two distributions basically. So this is actually the Kolmogorov Smirnov two sample test statistic for testing H0. Now naturally, if the two distributions are close, then naturally their sampled values will be closer to each other, and therefore there will be regions where Fm and Gn will be similar. So therefore the differences will be smaller, otherwise the differences will be large. So we can simply say that large values of Dmn indicate that H0 is false. So Dmn is actually distribution free. We will actually discuss the method how to determine the probability of type 1 error, type 2 error based on this thing. So this is distribution free. Let us discuss these methods now. So one method that has been discussed, it is actually by Hodge's method. Hodge's method for determining probability of Dmn greater than or equal to D under H0. So first thing is that we consider the combined sample. Consider the combined sample of x and y values, and then arrange it in increasing order. That means we rank them of magnitude. So we consider a Cartesian system in the following fashion. Depict on a Cartesian system of coordinates by a path which starts at the origin and moves one step right for an x and one step up for a y. So it is like this. If x is next, then we come like this, otherwise we go like this. So it could be like this and so on. So observed values of m, fm x and g n, g n x, they are actually all the coordinates of the points of u v on this path, where u and v are integers. Observed values of m, fm x and n, g n x, they are respectively the coordinates of all points u v on the path, where u and v are integers. So d is then equal to maximum of basically u by m minus v by n, which we can write as 1 by n v minus n by m u, we can express it as 1 by n into the vertical distance from the line nx minus my is equal to 0 to the point on the path which is farthest. So mn is a number of arrangements, that is paths of the sample which lead to dmn less than d. Then you will have probability of dmn greater than or equal to d under h naught, that is equal to 1 minus amn divided by m plus n cm, because m plus n cm will be all the paths. I mean, we can have the extreme cases when all the xi's are below all the yj's, or one could be in which the all of them are like 1 x 1 y, like that, all it could be like that also. So amn is the arrangement of the paths of the sample which leads to dmn less than d. Then it is the probability that dmn greater than or equal to d is 1 minus amn by m plus n cm. So to count amn, we have to draw two lines at a vertical distance nd from the diagonal and count the paths which lie entirely within these lines by use of the recurrence relation that is a u v is actually equal to a times u minus 1 v plus a of u v minus 1, and of course a u 0 that will be equal to a 0 v, that is equal to 1. Let us also consider this if mn tend to infinity such that m by n goes to a constant, then probability that dmn root mn by m plus n is less than or equal to z, it converges to 1 minus twice minus 1 to the power I minus 1 e to the power minus 2 I square z square, I is equal to 1 to infinity. So asymptotic distribution is obtained here for testing h naught versus h1, where h1 could be like a stochastic ordering, that is say gyx is less than or equal to fx. Basically it means y less than or equal to x is less than or equal to probability x less than or equal to x. That means basically what we are saying is that x is stochastically large smaller than the x is stochastically smaller than y, and for all x, and say gyx is less than fx for some x. So one uses a version of this, let us call it dmn plus, that is maximum of, that means we consider only one sided, maximum of fmx minus gnx Hage's method can be used to find probability of dmn plus greater than or equal to d under h naught for small values of mn with obvious modifications. One can talk about the full-fledged asymptotic distribution of dmn plus also. Let me give that here. Limit of mn tending to infinity such that m by n is a constant of the probability root mn by m plus n dmn plus is less than or equal to z under h naught, that is 1 minus e to the power minus 2 z square. We reject if dmn plus is greater than or equal to c alpha, where c alpha is determined by probability of dmn plus greater than or equal to c alpha under h naught is equal to alpha. To test h naught against h1 gyx greater than or equal to fx, for some x we interchange the role of x's and y's in the above. So basically you can consider here gnx minus fmx, and then similar thing will be holding here. Another concept is that of efficiency of the tests here. Efficiency of test, like the consistency of tests, like consistency of estimators, we have an analog of the efficiency of the test. So first is the power efficiency. Let us consider that. Power efficiency. These concepts I am introducing because in the usual classical theory of testing of hypothesis in the parametric situations, we have the concepts of the most powerful test, uniformly most powerful test, unbiasedness and other things. Now, when we are dealing with the distribution free situation or the non-parametric situations, then certainly those type of most powerful and other concepts are not valid, and therefore we need to look at the asymptotic properties. So that is why consistency, and now we are talking about the efficiency of this. So first thing is that about the power efficiency. So let us consider, say, omega is the parameter space here. So suppose I have a point, a subset of omega. So we are considering the hypothesis testing problem h naught theta belonging to small omega against h1 theta belongs to capital omega minus small omega. So let us consider, say, Tn and Sn. So let me put Sn star here, be two sequences of test statistics. We considered it sequence because they are based on the sample size, and so sample size may vary, that is why we are calling it. For testing h naught against h1. So here n and n star are the respective sample sizes. So let us take an arbitrary point theta star belonging to alternative hypothesis set. So let us consider Cn is the size alpha critical region for test Tn, and let us call say Dn star is the size alpha critical region for test Sn star. So now let us consider probability of Tn belonging to Cn. Then this will be certainly less than or equal to alpha for all theta belonging to omega, and probability of Sn star belonging to Dn star, that will be less than or equal to alpha for all theta belonging to omega. So these are two size alpha tests, and critical regions are identified by Cn and Dn star respectively based on Tn and Sn star. Let us consider now the powers here. Let us fix a power say beta, and suppose we require n and n star as the sample sizes. That probability of Tn belonging to Cn star this will be this, that is equal to beta under some value say theta star. Then, and here this theta star belongs to actually omega minus omega. So then the efficiency of Tn with respect to Sn star, this is for fixed alpha beta and theta star. This is defined as ETS is equal to n star by n. So naturally you can have the interpretation here. So for example, if ETS is greater than 1, if it is greater than 1, that means for achieving the same level of power I need more observations in S compared to T. That means T is more efficient than S. If this is less than 1, ETS is less than 1, then it will mean that I need more observations in T compared to S for achieving the same level. So T is less efficient than P. So we can write that. So ETS greater than 1 implies that we need more observations in test based on S compared to T for achieving same power. So T is more efficient than S. Similarly, ETS less than 1 implies T is less efficient than S. So for this efficiency we have some sort of interpretation here. But of course this definition is having a limited usage here, because we have fixed here alpha, beta and theta star. If we change the theta star and the underlying distribution changes here, then I mean for different underlying distribution this may be quite complicated to adopt here. But anyway, this is a definition. Let me consider some example here. Let us consider the usual problem based on say normal distribution, say normal theta 1, and I consider h naught theta is equal to 0, h1 theta is not equal to 0, or say theta greater than 0, for example, let us take. So, let me take theta star in the alternative hypothesis set as 1. So, the usual normal test is okay, usual normal test, that is reject h naught if root n x bar is greater than a n, basically that is z alpha. So, if I am taking say alpha is equal to 0.05, then a n is equal to z 0.05, that is equal to 1.64. So, if I consider say probability theta star is equal to 1, root n x bar greater than 1.64 is equal to say 0.9. So, I am taking say beta is equal to 0.9, say for example. So, this will mean probability root n x bar minus 1 greater than, so this will become 1.64 minus root n is equal to 0.9. So, that means 0.9 is equal to 1.64 minus root n is equal to minus 1.28. So, this you can simplify. So, this is n is approximately 9. Okay. Let us take second test, say based on the sign test function here, S, say usual sign test. For usual sign test, you are saying reject h naught if k n is greater than d n. So, let me put here star. So, if I am taking alpha is equal to 0.05, and so okay, let us say f x 0, that is equal to probability x greater than 0, that is half. If theta is equal to 0, it is equal to 1 minus phi of minus 1, that is approximately 0.85 if theta is equal to 1, for example. Okay. So, now we are having two equations, sigma n c I half to the power n, that is equal to 0.05. This is for I is equal to k plus 1 to n. This is one equation, and the second equation is sigma n c I half 0.85 to the power I and 0.15 to the power n minus I for I is equal to k plus 1 to n, that should be equal to 0.9. So, you need actually to solve these two equations to get the value of n, and actually k is also required here, because at which point that cutoff will come. So, solving 1 and 2, we get n is equal to 15 and k is equal to 12. So, what we conclude then? So, efficiency of normal test corresponding to this one will become equal to uh, 15 by 9, that is equal to 5 by 3, that is equal to 1.67, etc. So, basically it concludes that the usual UMP test based on normal distribution is more efficient than the sign test. Now, this is under the information that under the assumption of normal distribution. If the normal distribution is not there, then certainly you cannot use this, under the assumption of normality. So, if the distribution is known, certainly we will use that information. Now, This is for the power 0.9. If we use some other power, say 0.95 or 0.92, then certainly this efficiency level will change, but certainly it means that the test based on the normal test is certainly more efficient than the sign test here. Since this is completely dependent upon the values of alpha, beta and the point that we have chosen, there is another concept that is called the asymptotic relative efficiency of the test. Let us consider this concept now. Asymptotic relative efficiency. Let Tn and Sn star be two sequences of test statistics for testing the hypothesis h naught theta is equal to theta naught. This is fixed against the alternative theta belonging to some gamma, and we are considering level alpha and theta i's. This is a sequence of alternatives to h naught such that theta I converges to theta naught as I tends to infinity. So, we are considering alternatives, but they approach the null hypothesis value. So, let us now consider say beta Tn theta I and beta Sn star theta I. So, these are the power of tests based on Tn and Sn star at theta I. So, T is based on n observation and S is based on n star observations. So, we consider this Ni and Ni star sequences, and I consider the conditions such that Ni and Ni star increasing sequences of natural numbers such that 0 less than limit as I tends to infinity beta Tn I theta I is equal to limit as I tends to infinity beta Sn I star theta I is less than 1. Then the asymptotic relative efficiency that is ARE of T with respect to S is defined as ARE Ts is equal to limit as I tends to infinity Ni star divided by Ni, provided the limit is unique for all sequences Ni and N star which satisfy this condition star. For all sequences Ni and Ni star satisfying the condition Okay, so what does it roughly mean? It roughly means that suppose I say this value is equal to say 1.2, then it would mean that in test based on S I need on the average 120 observations if there are 100 observations needed by the test based on T to achieve the same level of power. So, now since this definition is a limiting definition, this is you can say a better definition than the definition of efficiency which I gave just before this, because that was a fixed sample size definition here, and here it is an asymptotic kind of definition. Now, there are several ways of calculating the asymptotic relative efficiency. Let me briefly mention about that. Methods for estimating the asymptotic relative efficiency. So, we are having two test sequences. So, we have the hypothesis testing problem, theta is equal to theta naught against H1, theta belongs to some gamma, and we have Tn as a test sequence and Sn star is having another test sequence, and we assume that both are level alpha consistent tests. That means they are one sided, let me say, and large values are significant. Basically, it means that we are having right handed critical regions, right sided or right handed critical regions. This is just for convenience, otherwise to compare two tests it will become quite complicated. So, let us consider that say expectation of Tn is say mu Tn theta, expectation of say Sn star that is equal to mu Sn star theta, variance of Tn say that is equal to sigma square Tn theta, and variance of Sn star is say equal to sigma square Sn star theta. So, let us assume that let T be a random variable with absolutely continuous distribution function Hx for all theta belonging to gamma, and we assume that the asymptotic distributions of standardized variables of Tn and Sn, they are based on T. They are basically T, we are saying that they converges in distribution to T as n tends to infinity. We also assume that Sn star minus mu Sn star theta divided by sigma Sn star theta converges in T. Let theta I belonging to gamma be a sequence such that theta I goes to theta naught as I tends to infinity, and let Ni star be two sequences of sample sizes such that 0 less than limit beta Tni theta I that is equal to limit beta Sn I star theta I tending to infinity is less than 1. So, let us take say alpha to be between 0 and 1 and let the critical region points be such that probability of Tn I greater than or equal to Cn I, that is equal to Sn I star greater than or equal to Dn I star is equal to alpha. So, then you can consider here 0 less than limit of beta Tn I theta I as I tends to infinity, that is equal to limit of probability theta I Tn I greater than or equal to Cn I as I tends to infinity. Now, based on the asymptotic distribution of Tn I, we can express it as limit as I tends to infinity probability of theta I Tn I minus mu Tn I theta I divided by sigma Tn I theta I greater than or equal to Cn I minus mu Tn I theta I divided by sigma Tn I theta I, that is equal to limit as I tends to infinity beta Sn I star theta I, that is equal to limit as I tends to infinity Sn I star minus mu Sn I star theta I divided by sigma Sn I star theta I greater than or equal to Dn I minus mu Sn I star theta I divided by sigma Sn I star theta I, that is less than 1. So, if we compare the let me call this as so from these two relations we get this imply that limit as I tends to infinity of Cn I minus mu Tn I theta I divided by sigma Tn I theta I is equal to minus Dn I star minus mu Sn I star theta I divided by sigma Sn I star theta I is equal to 0. Okay, so one way to implement this is to assume all terms to be 0, that is Cn I minus mu Tn I theta I divided by sigma Tn I theta I is equal to Dn I star minus mu Sn I star theta I divided by sigma Sn I star theta I for all I, and solve for Ni by Ni star. Then ARI of Ts is equal to limit as Ni star by Ni for I tending to infinity. That is one way. Now, to go one step further, you can assume that Tn and Sn star have the same limiting distribution for all theta. If that is so, then you will have alpha is equal to probability theta naught Tni greater than or equal to Cni is equal to P theta naught Sni star greater than or equal to Dni star. So, this will imply that limit as I tending to infinity Cni minus mu Tni theta naught divided by sigma Tni theta naught minus Dni star minus mu Sni star theta naught divided by sigma Sni star theta naught, that is equal to 0. So, if we equate each term, then we can again define. Equating each term, we can get the ARE. We can also assume so let me just briefly mention these things, because all of them are leading to additional conditions here. We can also assume the standard deviation. That is this one. That is equal to 1. Then again we can get the condition here. So, these are the methods for estimating the asymptotic relative efficiency. There are certain results regarding this, but I am not getting into this thing. In non-parametric statistics, I have discussed main methodologies, that is based on the, firstly we discussed in detail the role of the order statistics, asymptotic distributions of the order statistics under various conditions. We also discussed the estimation of the distribution function based on the empirical distribution function. We considered the ranks, the distribution of the ranks. Based on the ranks, we considered several 1 sample and 2 sample testing problems. Basically based on the location and scale, we gave certain tests. Towards the end, I have introduced the concepts of asymptotic relative efficiency, the concept of the efficiency of the tests. The subject of the non-parametric tests, or you can say the distribution free procedures, is quite vast. It has developed a lot in past 50 years, and there are various other aspects of it. For example, there is a huge class of problems which is known as the Hoeffding's U statistics. Let me briefly mention about this one. We will very briefly talk about the Kruskal-Lewis formula and also the say Kendall's, Tau and Spearman's thing. In the remaining 5 minutes or so or 10 minutes or so, let me just briefly mention about these topics. There are other things like density estimation based on the kernel methods, and there are so many other topics that have developed over the past few years in the field of non-parametric, but in this particular course we can cover only this much. Maybe in another course we will discuss in detail about those procedures also. So, let me talk now about the Hoeffding's U statistic. So, what is a Hoeffding's U statistic? Hoeffding's U statistic is defined as that let f be a class of distribution functions, a parameter theta is said to be estimable of degree m if a random sample x1 x2 xn n greater than or equal to m, there exists a function h of x1 x2 xm such that expectation of h of x1 x2 xm is equal to theta. So, this is based on this we define a kernel. So, h of x1 x2 xm is called a kernel. Now, based on this we can define a Hoeffding's U statistic as 1 by n Cm sigma h star x beta 1 up to x beta m by taking all the permutations of, that means by taking all m permutations from n here, that means we based on that. This is called a Hoeffding's U statistic. So, this is actually the name of this. So, basically this is a symmetric function in its arguments, and you can actually see that most of the standard estimators in the parametric situations and also in the non-parametric situation like sign test, Wilcoxon-Rankin test, Mann-Whitney test statistic, they will be actually based on the Hoeffding's test. The good thing about the Hoeffding's U test statistic is that the asymptotic theory is established, that means the asymptotic normality is there, and therefore, various procedures for this can be established for this one. As I mentioned, non-parametric methods are also applicable when the normality assumption is not satisfied. There are also situations like when we have large scale data. So, when the we are unable to fit a distribution, or it is impossible to say that which distribution will be applicable, because there may be too much variation when you are doing the fitting of the distribution, then certainly non-parametric distributions, non-parametric methodologies are used. One of the important methodologies, for example, you can think of is the in analysis of variance. In analysis of variance, we assume that the errors are normally distributed, but if the normal errors are not normally distributed, then we go for a distribution free procedure that is called Kruskal-Wallis test. So, Kruskal-Wallis test procedure is based on the again ranks here actually. So, if the ranks are there, we are considering let me just very briefly mention about this one. So, we have k samples, and the sample sizes are n1, n2, nk, and n is equal to sigma ni. We consider the all the observations mixed up, and we consider that Ri is the actual sum of ranks based on XI1, XI2, XINI in the combined sample. Then you define the statistic Ri minus Ni divided into n plus 1 by 2 whole square, I is equal to 1 to k. So, this is actually for the Kruskal-Wallis, and then we define H is equal to 12 by n into n plus 1 by Ni Ri minus Ni into n plus 1 by 2 whole square, I is equal to 1 to k. So, based on this the testing procedure has been developed. So, this is called the Kruskal-Wallis formula. The general linear rank statistic for k sample problems have been also defined, and then again versions of like van der Waals statistics, Terry test statistics, etc. are also defined. Another thing is regarding the coefficient of correlation or the coefficient of association, etc. So, we have the usual Karl Pearson coefficient, and the distribution for theory for that has been developed, which I mentioned when we were discussing the multivariate statistics, but again that is based on the normality assumption. If the normality assumption is not there, then we define measure of association and also a correlation coefficient which is based on the ranks. So, we have the two following things. One is called Kendall's tau coefficient, and another one is called Spearman's rank correlation. So, I will mention about this thing how they are used. For example, when we are discussing the same side concordance or discordance, then Kendall's tau coefficient is used. For example, we are seeing which side the values are, like xi less than xj, then yi is also less than yj. If xi is greater than xj, then whether yi is greater than yj. In such cases, the Kendall's tau coefficient is used here. And there are other situations, like we are considering the coefficient of correlation, then it is based on the observed values xi yi, that is x1 x2 x1 y1 x2 y2 xn yn are taken, and we based on this we define the coefficient. But here the actual observations are used. That means, for example, we may be considering weights, we may be considering heights and so on for two sets of this one. But suppose we are not interested in the actual values, rather we are interested in the ranks, because it could be a measurements may be related to something which may not give actual picture. For example, if you consider the how much agreement is there between the ranks given by two judges for ranking certain athlete. So, for example, some gymnastic competition is there, and then so there are several competitors and there are 3 judges or 2 judges are there. So, those 2 judges will give ranks on the basis of each performance. Now, then whether there is an agreement, that means whether they are on the same side, that means a good performance is appreciated similarly by the 2 judges, or they are biased, that means whether one judge judges one candidate as better compared to the other one. In such cases, we use Spearman rank correlation coefficient, and it is much more useful. We end this course at this note. As I mentioned that there are so many other things in the statistical methods for scientists and engineers. There are so many new methodologies have been developed. For example, large literature is available in the regression methodologies, time series and other things, but of course, then certain other courses will be available for that. There is a vast area of Bayesian methodologies and frequentist decision theory. So, one may look at those topics for applications. I will end this course at this particular note.